All right then. So let's move on to a related idea, but still similar. So we're just going to extend exactly what we've just done here, but thinking about what happens if we, instead of taking like whole number powers, we take square roots or cube roots or things like that. Okay. Now, in order to do that, we're going to take ourselves back to thinking about the real numbers, because as with most things, we have a grasp of the real numbers, a really solid grasp of the real numbers. So therefore, a lot of the, because complex numbers are just numbers, if we can understand what happens with the real numbers, the complex numbers shouldn't be too much work. Okay. So let's give this one a go. Yes, of course.
In every example, we didn't take the power of numbers bigger than 4.
Right.
If we take, let's imagine that we are taking the 6th power of any complex number.
Yep.
In every 4 times, it rotates and comes to itself, right?
Maybe. Okay. It depends, because that only happened because we were dealing with I, right? So you said, okay, every 4 times it repeats. Only true with I, right? Because if you think about it, I, by rotating by I, you're rotating by pi by 2, right? So 4 times by pi by 2 is going to give you, well, 2 pi, isn't it?
And 2 pi is a whole circle.
Exactly, 2 pi is a full rotation. Okay?
Basically, it's not by 4, it's when it goes by 2 pi, it resets.
Yes.
Can you say again, sorry?
Yes, absolutely.
It depends on your argument.
Yes.
Is that right? Yeah. So if the argument is, let's say, pi by 2, if you do it to the power 4, it will reset. But if your argument is pi, every 2 power it resets.
Exactly.
So the fact of your argument will depend.
Okay. Yeah,
So it's all to do with the argument, absolutely. So for example, I mean, yeah, absolutely right. Multiplying, the argument was pi by 2. If you multiply that 4 times, the reason why you reset it is because that comes out as 2 pi, which is of course a full turn, right? But say, for example, if your argument was pi by 6, right? Then in other words, if you had a complex number where your argument was pi by 6, if you raise that to the power of 6, in other words, you'd multiply this 6 times, then you'd end up back where you were before, because that's 2 pi. Sorry, that's 12. Sorry, that was my mistake. If you raise it to the power of 12, so you take a complex number with an argument of pi by 6, raise it to the power of 12, then basically you're going to end up with a complex number that is the same orientation as it was before, but of course its modulus will be different. Yeah. But yeah, so good. You're kind of thinking about that. Fantastic. Okay, so like I say, we'll move on to thinking about powers of complex numbers. Now, like I say, think about real numbers and then we can extend it to the complex numbers. So for example, if I take x and if I raise it to the power of 1 and I'm supposing that equals 1, what's the solution of this equation? Something to the power of 1 equals 1. What's that got to be?
X equals 1.
Good. Okay, nice and easy. Okay, what about this one? X to the power of 2 equals 1. What's the solution of this equation?
Minus or plus.
Good.
Square root of 1.
So it's positive 1 or it's negative 1. Fantastic. Okay. All right, let's try this one. X to the power of 3 equals 1. Solution.
I think it has to be more.
Good. 1 cubed is definitely still 1.
I can't say for -1.
No.
It's not negative 1 because negative 1 cubed is negative 1. Is that it?
No.
Why not?
No, I can't explain this thing.
Okay.
X to the power 4, I could say it's -1 and 1 again.
Okay, let's go for that one. So x to the power 4. So we're kind of unfinished here, so I'll just put question mark here. Or we think we're unfinished at least. Okay, so x to the power 4 equals 1. What are we supposing the solutions are?
So it would be 1, 1.
Good, x equals 1 or x equals -1. Is that it?
I think there's others, but I don't want to say.
You're right, there are others. Now, what I'm talking about here is something called the fundamental theorem of algebra. And actually, this was derived by, or this was discovered by somebody called Carl Gauss, a very famous mathematician. Did a lot of work. You know Gauss?
Yeah.
Right. Okay. Did a lot of work with a lot of work with number theory and stuff like that. But yeah, this kind of idea.
His teacher kicked him because he was stupid.
Exactly.
Yeah. The guy.
You know the story, right?
Yeah.
So they said, so this teacher, because he was a genius, and because the teacher got frustrated because they're like, he just knows all the answers to the questions. And they said, I know what will keep him quiet. Add all the numbers from 1 to 1,000 together. And like 5 seconds later, he said, it's this. I think it's like 50,050 or something like that. And they're like, why'd you do that? And of course, because he realised the pattern behind it, realised the fact, if I just take like 1 to 100, so 1 plus 2 plus 3 plus etc, plus 97. I'll start 99, 98, 99.
Oh,
Yeah, and he realised the fact.
What?
The number, divide by 2.
Perfect. He realised that if you pair the ends up, so 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101. So basically, if you kind of work your way inwards, they always add up to 101. So you have like 101. Then you just realise how many pairs do you have? Well, if there's 100 numbers, there's got to be.
Himself?
Yeah. And he was only like
That's
6
right.
or 7. Yeah, I think he was only 6 or 7 at the time. So an absolute genius. But so that's kind of it. So yeah, 50 times 101 is going to give you whatever that is, 50,000 and 5,050, I think. But yeah, Gauss, very, very famous guy. But he also did a lot of work. In fact, he came up with one of my favourite quotes in mathematics, which is, we should think deeply about simple things. So the idea is you look at something and it looks simple, but actually when you really look at its fundamentals and its kind of links and connections together, it's fascinating, and it kind of unveils a whole new way of thinking. But yeah, he basically came up with this, which was the fundamental theorem of algebra. And he literally said, if you're trying to solve an equation of this type, where you have powers involved, so you have unknowns raised to different powers. Does anybody know what family of equations these are, or these belong to? Polynomials? Maybe? Okay. So yeah, they're called polynomials, right? So basically where you have x's are your unknowns, you're raising them to different powers. I mean, for example, quadratics. X squared plus 3x plus 4. Right? That is an example of a polynomial, okay? In fact, if I made that negative, it'll come out quite nicely. So these are examples of polynomials. Basically, you have unknowns being raised to different powers. And basically, what Gauss established was, if you look at the highest power of the equation, because of course you may have other terms in here. You may have, for example, x to the power 4 plus 3x squared plus 5x, right? If you look at the highest power, that will tell you how many solutions you are expecting, okay? So we call this the order or the degree of our polynomial. That's just simply the highest power. So if you look at the highest power of your equation, that will tell you how many solutions you are expecting. So here we said, I don't think we're finished when we just came up with x equals 1. It's definitely a solution, because if you look now, given the fact the fundamental theorem of algebra exists, if we have x to the power 3, how many solutions are we expecting? 3, right? So we've only got 1. So the question is, where are the other 2? Similarly, when we had x to the power 4, how many solutions are we expecting? 4. We only found 2. Where are the other 2? So there's equations missing. The solution's missing. Does anybody want to hazard a guess where we should look for these equations?
Maybe imaginary.
Good. Complex numbers, right? At the moment, you're just giving me real numbers, yeah? Now, they're fine. They are valid. But if you want to find the other ones, you have to know about the imaginary numbers, yeah? Or the complex numbers. So that's what we're going to look at now.